Uh-oh. Caught the attention of someone. It's the famous Simon Tracer, physicist, scientist extraordinaire, thought provoker, dude who talks about how you can be heavier and you sink better than if you are lighter, and a bunch of other facts. Neil, but it's not just you, it's everyone. Let's face it, it is everyone. Talking to all you. You know the title of this video. Now you gotta be like, okay, he has to be tripping. He has to be like, how can he come to this conclusion that time doesn't dilate? Like, I got this video out there, says time dilates. Okay, alright, yeah, yeah. Oh, and the other thing, right? So it's the way he said it, because I just saw the video. Two things happen. One, you have a gravitational field, and two, you have speed. So the speed of the object, or the gravitational field that it's in, is said to affect how the clocks work. No, he said it affected space-time. What's the difference? There's a difference. It's a mechanical versus the entire fabric of the universe difference. And the distinction is kind of important because if you start going ahead of yourself and saying that space-time is affected by speed or by gravity, you're forgetting not to oversimplify or great. You're forgetting that great what is the actual terminology? After you remove everything else, what else is remaining must be the truth. So, have you eliminated everything when you say these things? Well, the other thing is you have okay. So we talk about. I'm saying it affects the clocks, like mechanically. Now, why would that happen? Well, you look at what happens when you start having any object go at literally any speed. For example, this tissue currently is just floating in a soft breeze from the fan. Drag it across, and it is pulled along, and it floats more, and really, it really wants to stay straight as it floats and is hit with more air resistance and stuff. Speed affects its function or its actions through space. And that's low speed. Am I manipulating space time? Everyone would say, clearly not. Exaggerate the situation into moving at speeds or gravity effects that are like out in space versus here on the planet, and you can see how people lose sight of the fact that even low speeds will affect an object, its motion, its function, its available um, ways of behaving. So I established with a tissue, right? I've established with a tissue, not to be confused with a brand, but just anything. Paper, you know, paper is easier, because naturally paper is stiff, but it'll just hang down, and when you go faster, it just raises up. It's the same with a tissue. So you can do this at home. You just fling a tissue around, and be like, woo, and it wants to go in this really straight line. It doesn't drag down, right? It's affected by wind resistance and stuff, and therefore it does things differently. And so when we exaggerate this and we say clocks out in space going at crazy speeds, where all of this push of gravity or speed, which it's the same thing. It's the same thing. It's not the fact that there is some weird distinction between going fast and being pulled by gravity. No, it's the exact same thing. And I'll tell you why. You're on a planet, it's moving fast, and it's pulling you around. You're going at a speed. Once you start going at a different speed, you're going to be affected by the forces of relative everything else to you, right? For example, if you go, there was one other video that talked about the idea of there are 3 different clocks. One was put on the ground, one was put on a jet that was going the same direction as the rotation of the Earth, and one was put on a jet that was going the opposite direction of the rotation of the Earth. And what happened was that they had both jets go at the same speed. Let's say it's 100 miles an hour. They went around the Earth in one direction or in the other, and the clocks all had different time. They were all same when they started, and they were all different. One was ahead and one was behind, and the other one, the neutral on the ground, it didn't change. So, why did that happen? Did space-time get violated between these clocks? I would say obviously no, because it's interesting. There's no difference in their speed, but at first glance, because according to instruments, they went at the same speed. But understand this, though. If you're going around the planet in the same direction as its rotation, it's, in my brain, analogous to if you are running up a train, right? Your speed and the speed of the train add together, and you end up seeming to go faster than the train, although your body is not pushing yourself faster than the train speed's added to you. Similarly, going the opposite direction of the rotation of the Earth is similar to going backwards on the train. Train's going this way, you're going that way. Or I should say this, and you're going that. To make it real easy to understand the idea that I'm trying to portray. So, what's happening? What all is taking place? And why was one clock ahead and the other clock behind? Well, altogether, as you're moving against it. Like I said, moving when you're moving at the same direction as the rotation of the Earth, the speed of you and the speed of the Earth add together. So you get that little bump of extra force that you should experience due to the accumulative extra speed. The other plane going the opposite direction, the force of it was the opposite and it negated from their total force experienced, so therefore they had their clock be a little bit behind. Now, regardless, it doesn't matter if I'm correct about which one was forward and which one was back. The reasoning for why it happened is that one of them had more force than the other, and that's how it ended up with the higher and lower amounts of speed and higher lower amounts of the actual time. This is a nuclear clock. So it was off. Each clock was like a fraction of a second different. The one clock, the neutral clock that stayed on the ground, was one way. The one clock that went same direction as the rotation of the Earth, I think it either sped up or it slowed down a little bit. And then the other one did the opposite. So that tells me that forces were applied to the clocks. One where it was added and one where it was subtracted by going in one direction, going the other direction versus the rotation of the Earth. And the reason why I mention it as if it's a new idea is because the way that I heard people talk about it is that they only attribute speed. They don't think about, for some reason, the forces that are affecting the clocks themselves. They don't think about, like, for some reason they're saying it's some kind of time dilation. But time's not changing, is it? You realize, right? The more force applied to a string or a ribbon, the more it will wobble until at some point when you apply a lot of force, it'll be straight. You can't, once you go a certain speed, that ribbon is only going to be flying pretty much straight because all wind resistance is all pulling on both sides. It can't wobble. There's no gravity weirdness happening. Or there's no gravity that can affect it enough. It will all pull down. Maybe. And droop a little bit. But it'll be mostly straight. Versus if you let it go slowly, the ribbon is able to wobble and do its thing. As the fan that's far away is capable of moving this, that's basically what it's like for that ribbon that's going slowly. But then you move it fast and it glides through the air. When you look at these clocks, you look at the motion of what all is happening in the clocks, right? Zoom in, zoom in, zoom in, zoom in, zoom in, zoom in, and you got the atomic, and suddenly you're looking at electrons that are zipping around the atoms that are being scanned, and as they scan, I think it's a beryllium isotope that has a very specific resonance, right? But resonance can be affected by motion. You could punch the clock and have it be offset. And if you punch it in one direction, the force is experienced and it should happen to have a certain effect. You punch it in the other direction, don't punch clocks, but if you did punch it in the other direction, it would be jostled. And there would be basically no difference between you punching it forward and backwards because relatively it's just being jostled, and that is one type of motion, just basic general jiggling. It's not great. It doesn't give you any information, but it tells you that a force applied makes the thing go not correctly. Okay, so now we apply the force. We say that there is more force in one direction and less force in the other direction. So it's able to, if it's able to move more freely in the other direction, it will. And if able to move less freely in the one direction, then that's what it'll do. And what happens is exactly that. Stuff gets all scrunched up and compressed. And on a macroscopic level, we can understand this and we can see this and it makes sense. Now, but on the atomic level, we forget about that aspect of life. And we think that these things should still operate the same unless time dilation. Put it in a centrifuge, it's not time dilation. Yeah, you shove a clock into one of those DNA centrifuge type things, and it'll spin it around at like maybe 4,000 RPM or whatever, and you'll experience that it don't know how to tell time correctly anymore. And it tells you a different story about what happened in time. But that's because you're messing with it. Same difference if you have it go really fast in a singular direction. Because really all you're experiencing in the centrifuge is if you've ever ridden one of those rides where they put you in a centrifuge, you're stuck up against the wall and you're like, it's fun, and you experience one force against you, pulling you back. It's like it is gravity. Everything's moving in a circle, but you're being pulled towards one side. This is why water in the bucket stays in the bucket even though you fling it around. It's being pulled towards the bottom. Similarly, an equal opposite sort of whatever blah stuff is happening with you and the planet. The thing is, the planet is so big and its rotation is so fast. You realize if you stop the rotation of the Earth or slowed it down slowly, gently, relaxedly, yeah, eventually if the planet just stops rotating, you end up with too much force on one side of the planet and everyone's just squished there. A bunch of sliding forces which force you to go up towards the edges of the planet, and on the other side where everything's moving away, you're just either floating with it or you're just gone. That's why having a rotating planet is really good for us. Slow down the planet to a certain RPM and we don't have gravity anymore, because it's not pushing on us in the same amount in all directions. See, it doesn't matter if we have ourselves literally every day, our momentum compared to our rotation around the sun is facing in the direction away from our motion in that rotation, in that orbit. We're actually facing that direction sometimes, but only sometimes, briefly. And it doesn't matter because we are constantly moving and the Earth is constantly pushing at us with that same force that we experience on the ride. It makes us do this. That's gravity. That's what gravity do. It's a spinny thing. You get pulled towards spinny thing. And why is spinny thing the best way for anything to go through space, or the most expected way for it to go through space? It's simple. If you have anything collide with another thing, they start to spiral. There's some kind of off balance in the collision. One hits it just a bit to the side or whatever else, and because they want to, if they all want to keep moving together, but because of collisions, they end up curling, just like rolling a ball or rolling a snowball up a hill. The ball ends up collecting, eventually ends up forcing everything even tighter and tighter and tighter as more things are colliding and being forced towards each other because you are all being moving through the orbit around the star and around the galaxy. You're going crazy fast right now. You just don't feel it. You feel like you're sitting on your couch doing nothing. You're going crazy fast relative to something. That's important. So once you start adding more speed or less speed, the forces applied are different. And they say that gravity isn't a force. That's because they're silly. They are silly. You moving through space, and then you hit something, forces are being transferred there. And the more you are allowing yourself to be moved towards that thing, the more you're going to deform and whatever else and stuff. Like when you see a slow motion of a golf ball being hit or a tennis ball smashing into the wall, it squishes. And then elastically it just goes back to normal. Or a ping pong ball does the same thing. You would think that a ping pong ball is very solid, but when you look it up, it actually squishes a lot when you hit it. It just turns back really, really fast. Now imagine stuff on a clock going at speeds, effectively hitting nothing, but still they're going at speeds. They are having forces of everything around them apply to them. So the faster you go, and here's the interesting thing: the slower time goes, because your rotation, everything else goes. They experience time as going slower because there are more rotations in their individual functions compared to when they're just moving slowly. You realize that as you're moving forward with a propeller, just any old propeller, it starts turning faster. The faster you go, the more it turns. The same thing can happen to electrons. They're hitting something out there in space. especially once they go at crazy speeds like 10,000 kilometers an hour. That'll affect it. And not only that, but because light is a regular thing that just doesn't give a crap about how it's moving through space, it will end up. Now, it would be so much better if I had visualizations about all this. I could explain it to you better. You'd grasp it more. You would be able to not need to focus so much with your imagination about it. But I'm talking to the people who already should understand science. And unfortunately are saying the lie of time dilation. You need to stop. I'm talking to you, Neil deGrasse Tyson. You're failing your exams. 2 million views. You're failing your exams because you say that explaining time dilation, and I'm explaining it doesn't happen. So then you go and you say, oh, what? But hold on. We put there's an isotope, or there is a muon, right? And the muon will degrade. It takes like 6 seconds or something, or 6 minutes. I don't know. I forget what he said. But then you put it in the accelerator where it goes at near the speed of light, and it said it took longer for it to degrade. You know why that is? Everything's held together more because more force is applied. If it's allowed to just bounce around and do its natural thing, it'll degrade in a predictable manner. If it's all being pulled in one direction, it's less likely that stuff can just bounce off. You understand how radiation happens, right? You don't? Okay, let me explain to you how radiation happens. Because it seems like you need a crash course in radiology. Yes, I know that stuff too. Inside an atomic nucleus and all of that, there's this extra energy. There's this extra packet, an electron or whatever, has fused into the atom itself. It's inside the packet of neutrons and protons. It doesn't like to be there, and it's bouncing around, and eventually it's going to find the electromagnetic weak spot, and it'll bounce enough times that it finally shoots its way out. It's like, I'm free. Because other times, like a little ball bouncing between a bunch of balloons, it's usually hitting the balloons, but if it hits the gap between the balloons, it can get out. Now, what happens if you speed that up in a direction? Well, its own force to push forward isn't faster than the forces that are pulling it back towards the other protons and neutrons. You would think that it would shoot out in the opposite direction really fast, easily. But it's actually held there, and it's the reason that it needs to eventually have this bouncing to get out. And if it's pulled at a certain amount of force, then its motion is pretty much relegated to just being in that corner where it's stuck and it can't get out yet. It doesn't have that exit velocity because the forces applied to it are stronger. And that's why it doesn't degrade as fast. Something similar could be what the actual reasoning is. And the thing is, when you talk about time, you best make sure that you account for all possible things. The forces applied on the particle as its motion is still as important, and you can't just say it doesn't happen. It happens. Just as much as the objects want to pull themselves all in a straight line if you move them fast enough. Stuff is happening on the atomic scale, and you can't just keep denying that or ignoring that aspect of reality, because that'll give you an F in my class. Okay, maybe an E because you're trying. You are trying. But we're not talking about something that's super hard to grasp here. And you've been at this for decades, so I'm bothered that you're still thinking time dilation is real. It's disturbing to me at this point. I explained away the different speeds affect the motion inside the clock and the stuff and the reaction times, so that you actually end up with different different times read on the clock if you're going fast enough or going slow enough, or relative to everything in the universe possibly moving in an opposite direction, so you're actually slowing yourself down to the point of near zero. But what happens if you freeze that clock or heat it up? People talk about hot and cold as just being the motions of the atomic particles. So if you freeze it or if you heat it up, that also affects the clock. Makes it more energetic, or it makes it really slow. And therefore, you're going to have the clock tick differently. Even atomic clocks will be manipulated by just hot and cold. It's not even speed that does this. So therefore, anything that can affect the speed of the object, anything that can affect the speed of the object on the atomic level, that's going to affect your clock, and it's not proof of time dilation. Time dilation is where you take all of the rest of what you experience, you negate all the other forces that you're aware can happen or should be noticeable, and then beyond all those reasonable doubts, you also notice time dilation. But you're not. It's easily calculable. Move sync fast equals move. And the same thing happens on the atomic scale, and I'm just disappointed. So that's the thing. And then you go on to say something about, well, you know how there's photons, and you just start going at the speed of light, and you take it to the nth degree of, like, if something is going so fast as it's moving faster, that time for it seems to be slower than for a photon. It must be moving not at all. So when it was emitted from the star, once it hits whatever it hits, it bounced off the window, hit my face, boom, and then it bounced off of that, hit the screen here, and the sensor in the camera, right? Photons are energetic motherfuckers. They'll just go wherever until they finally hit something. Now, you do that, and he proposes that the photon just doesn't experience time at all. It's like, I was born, I'm instantly somewhere. And the silly idea is that he says that it stops, that the photon hits a person's face or like their butt or something when they're suntanning or whatever else, and it's like it stops there. If photons stopped wherever they hit, we wouldn't see anything, Neil. This is the biggest error you could ever say on national freaking internet. Light doesn't stop when it hits something. It bounces until it hits your eye. It gets trapped in there, and that's where it stops. Or it gets stuck in between all the parts of the mustache, and the beard, and the hair, the fuzzy bits. Right? Light doesn't bounce off of that. It gets stuck. Unless it's shiny, then it bounces off anyway. Like my eyes, all shiny. No matter what part you're looking at. Unless it's the middle part, who cares how shiny it is? It's still gonna freaking like there's nothing happening in that middle part. It's there, shiny as frick, and it ain't bouncing nothing because it's going in there. It's stuck. It could be bouncing some, but not nearly as much as everything else around it. And so, or my nose, it's bouncing more off my nose, or you think it is. It's just a higher concentration from my nose than anywhere else. That's why my nose is shiny. Shiny nose. So, we now understand it's just a basic thing to get wrong, that the light that hits something and then it's just stopped there. That's just a statement. It's a throw off statement, and it's just blatantly forgetting the laws of the general understanding of how light works. And I can forgive that. But when it comes to time dilation, I can't forgive that. That's why I made this video. And so, Neil, you made a 10-minute video. I responded with a 40-minute video talking about in depth the different points that you mentioned in your thing. And I'm gonna be just saying, yeah, you got the more views. I don't care. The problem is you got it wrong. And who cares? Because eventually everyone will get it right. And the way he talks about it is like, oh, it's a thing and it's true about this. Instead, I'm saying person was wrong. And my opinion of person was wrong doesn't matter as much to people because all they want to hear about, if I just said, time dilation doesn't happen. Here's what actually happens with these experiments that you're doing. But you see, the thing is, yeah, I could have done that. I could have phrased it in a way that it's like, it's just a truth. But the thing is, when I'm noticing a thing that somebody's saying and I'm like, no, Neil, you got it wrong. Like your whole video, you're not even analyzing it properly. And okay, he's a stargazer, he might not, physicist, right? He knows things, or he does research, he's not lazy. How does he not know these things? Okay, the light doesn't stop on your face. It keeps bouncing until it hits like a dark thing. That makes sense. And even then, it might still be bouncing. Who knows? But when it comes to your eye, it stops. It stops. It pretty much is absorbed there, right? So, okay, you can be wrong about one thing. I didn't even mention a comment. You also got how light works incorrectly. It doesn't stop, but I'm going to do that now. Bounces into someone's eye, or we would see nothing. So anyway. Yep. So this is the video in question talking about Neil deGrasse explains time dilation. And so if you want to watch that video, it's charming. And it's neat to think about how these things work, but unfortunately you're not bending space-time with these experiments. And so if you understand that you're not bending space-time and forces are being applied to stuff, then we can't go forward with stuff assuming that somehow you're going to end up aging less or something, depending your speed. Right? Go fast enough and suddenly you're no longer aging fast. That doesn't happen. And that would be a proof against time dilation. Because it's said that our clocks, we would experience time going slowly, but time actually is going at a regular rate and everything else is moving fast. More stuff in each second for everyone observing. The person in that fast thing would see time moving slowly. For everyone, and the thing he totally gets wrong is he says for them it would seem like everything else is moving slowly. No, he says it wouldn't even move at all for a photon. It just zips right by. That's not how it works. You see, perception of time has nothing to do with your motion of time. Even though if you talk about the clocks running faster, more stuff happening each second in a second than is normal, right? Well, the clock says it's a minute and 10 seconds instead of a minute that actually passed. That's not good. So we have to adjust for it. And so, yeah, we adjust for it and we got the satellites up there, and he mentions that somewhere in the video. I think it's the third thing he mentioned. And yeah, you're doing the calculations and you do all of that and you make sure that the satellites are correctly adjusting for the time stuff that's happening to their clocks inside of their satellites, instead of what's happening on the ground. And this is why we're able to make correct course corrections and make sure that the satellites don't hit each other, make sure that the satellite's time comes back to us and we have the regular, it's the time here and it is the same time everywhere. We calculate for all of that and we make sure that it is correct. Because that's important. It's really freaking important. The thing is that you're calculating for a thing that is affecting the clocks. It is disconnected from which function is actually affecting the clocks. Is it momentum or whatever else and stuff? But you call it time dilation, but it's still unfortunately not. My definition of time dilation is where, for me, everything else is moving really slowly. I'm moving really fast. Sure, that's time dilation. Opposite thing happens. That's time dilation in the opposite direction. So the thing is, if your Uncrustables get stale, It's all crust. Yeah. Don't let them get stale. It'll all be crust. That's what you have to come back from this. Don't let your Uncrustables become crusty everywhere. It's literally like you can hear that. It's a ting to it instead of a flat. It's not soft. I let it out too long. It touched the oxygen, stuff happened, reactions happened, it turned into crusty. Everywhere is crusty. What is it? What do you call that? That's crust. The little bit on the edge right here, the pinched part. That's crust. It's not brown. It's not crust. It's still crust. It's still crust. So, so what does this mean? This means that when you go at certain speeds, eventually you'll still find out that you won't experience time any differently. In fact, if everything's happening faster, the faster you go, relative to everyone else, it means your metabolism's going faster, which means you're going to age more as you go faster, not less. Because metabolic processes and all of that stuff, you can expect it to happen faster. Reactions happening faster, and everything's bumped against each other a little bit more. You're experiencing more of a reaction system. It's not going to just stand there and be happening on a slow basis. Okay, so the other thing is the experience of time, the flow of time. There is no difference in experience of the flow of time. If you properly have it calculated and everything, you won't experience it as going slowly or fast. The only way to do that is to make a person go at a percentage of the speed of light to the point where it's actually noticeable that, oh, we should see everything going by slowly and we can move faster. You know, when you put yourself in one of those centrifuges, you can't move at all. Everything's pulling you towards the back of the seat. You're not moving faster. So you wouldn't be able to speed up that. Therefore, time dilation is not what is happening. Otherwise, you'd still be able to move. Am I the only one understanding this? You move less. Meaning, if I wanted to experience proper time dilation, if I'm running a marathon and time dilation happens, I will be running that marathon, and for me, it'll be like everything's happening slowly, but for you, it just instantly is done, right? That's time dilation. But if I'm stuck against my seat, I can't run a marathon. I can't do anything. So it's not time dilation. It's forces affecting matter. Please get it right. I'm just so I can't. Where did I get all this? Why do I think it's okay to act like this and be this upset? Hank Green. He's been pretty upset recently. Frustrated. He's like, okay, people with climate change, man, they think either one, it's not happening, two, if it's happening, it's not our fault, And three, well, we don't really need to deal with it because it'll be fine. You can't say it will be fine and also say it's not happening or stuff will, well, yeah, but you can't say it's not our fault and also say it's not happening. Why would it matter if it's our fault or not if it's not happening? Clearly, you're saying, well, now it is happening, but it's not our fault. And so that's frustrating him. And I can get it because it's the cause and effect and an understanding of stuff. It's like when you try to tell someone, um, it's like the whole issue of what happened with me in the GTA sub server, the GTA roleplay server with Discord and 5M. It's like they took what I said as being passive aggressive or as me threatening someone, and I've tried to explain, um, sorry that you see it as me threatening you. That's you overreacting. I'm not meaning it in that way at all. I'm just really disappointed in your administration logic. Like, why do you think it's okay to treat us badly? Okay, it's okay for you to have a bad day. Bad days happen. I can forgive that. It wasn't just a bad day, though. It was a bad day that turned into a bad week, and it's also a bad month. And it's like, okay, if you explained that you're going through stuff, I can be considerate and be like, okay, it's a bad month, which it can be. It could be a bad year. It was for COVID. It's a freaking bad year. Everyone hated it. So if you're having a bad amount of time, mention it. That helps me be more considerate and stuff. But Kate, you failed in basic communication, basic humanity. I tried to be a friend, you treated me like crap. And so you say I got banned. No, I left. And I'm sorry that my friend didn't tell you that you treated me badly and really shouldn't be. Because, like, you thinking that I threatened you? You're going way too far. I said you deserve to be fired. That's not a threat. That's an assessment of your current situation. It's like either get fired or learn how to do your job right. It's not a threat. It's just me saying do better. If you're gonna say me saying do better is a threat, then it's like wait, just use your feet when you're climbing the stairs. Do better. Don't trip. Ask for help if you need help climbing the stairs. As an example, you know, handle it better. If you're stressed out and you're trying to talk to people about issues in the game and those things are stressing you out, guess what? Take a vacation from it. Take your mind off of it or get a better perspective of it. If I'm dealing with a lot of issues with the subserver or whatever else, I'm going to be telling people, you know what? Here's how it works. You mention issues. For me, it gets put on a list, and I deal with it when I have time to deal with it. Very casual, very simple way of handling it. You don't have to be all frustrated about it. So what is the difference between time dilation and what reality is happening, and when will it affect us? Well, the answer is it's not going to affect us anytime soon. In order for it to actually once it starts affecting us, is when we try to move something at a relative speed or whatever else, and we think that it's going to have this effect, and it doesn't. And that's going to be like for people trying to get to Mars or something at a fast speed or something. And wait, so if time isn't relative, if it's everywhere, if it doesn't matter where you are or what speed you're going at, time is the same everywhere, then that means that the black hole ideas don't work. You put something near a black hole, it's an amazing amount of gravitational force. You should expect time to be slowed way down for the person in that experience. Even if to an outside observer, they're moving really fast towards the black hole. But there, if you're there and experiencing it, it's like it's moving real slow. That's not how it works. So if you ended up being flung towards a black hole or even past it, you might get a bit of a angle trajectory change as you're moving past the black hole, and then suddenly, whoom, you're past it. But you're not going to be like, oh, I get to see the black hole for like a million years, and then suddenly I'm past it and time is normal again. That won't happen. You won't be able to do like tons of research near a black hole and be like, oh, I was there for like 10 years. And you're suddenly way older. And you have all these memories and experiences and recordings that took place. That won't happen. Sorry to burst your bubble. And it's just like, okay, it's silly. It's like no one's gonna actually experience this kind of thing for another 100 years or a couple decades. Why does it matter if he's wrong? We'll get the facts right when it becomes important to have that fact. Well, it'll eliminate. The other thing is it eliminates time. It eliminates a type of time travel where if you were able to manipulate time enough in different ways and make gravity or motion be all crazy, and then stuff like it's possible you'd be able to send a message backwards in time. Or it's possible you'd be able to have, that fast amount, that rapid research all done in split second. Your computer's running extremely fast, and whatever else you want it to do. It's like you were there for like a few minutes, but then it did trillions of years of processing. Not just because it's doing a lot of those per second, because of the weird way that the time's working. Like what's happening in the processors of the satellites. Whatever. This has been another Science Me video. You can check out all the Science Me stuff um, over in the playlist. I will keep on making these because I think people need to understand reality, and I'm willing to help. Like I love the idea of showing off stuff that I could do some research and I could talk to you about it. It's like, oh, this thing about there was the one topic recently. I hear a bunch of people talking about either what is it, nematodes or ants and stuff, and they end up moving in a circle, a big circle that no one understands why they're doing that. And the reason was explained in a different video. So go look for that.